Hi, I'm Yejang, a graduate student at UW Medicine. Here in medicine, we have three big lakes and you can walk on the lake, just like me. Well, during the winter, you can't. In winter, the lake freezes and the water turns into ice, which is an example of phase transition. In this case, from a liquid phase to a solid phase. Then, what is a phase? Phase is a form of matter such as solid, liquid, or gas. These are three main phases of material. When heated or cooled, matter can transition between the phases. For example, if you heat solid ice, the heat energy breaks the bond between the molecules, causing the molecules to rearrange and become liquid water. And it happens in reverse direction. When you cool it down, which is called freezing, where the freezing starts as lowering temperature is called freezing point. Below freezing point, the solid ice has forces between the molecules which hold them together tightly as solid, and the particles have an order with the attractive force. Thus, ice is a crystal. We're going to show you some very interesting phenomena with water and its freezing behavior, which we can understand this behavior by separately considering what is possible from how rapidly something happens. Now, let's start by making some ice.
Hi, my name is Enran. As Ye Zheng just said, water turns into ice below its freezing point, which is 32 degrees Fahrenheit or say 0 degrees Celsius. If we put a bottle of water into the freezer, we can expect based on thermodynamics that it would freeze. But how long would you expect this process to take? 10 minutes, an hour, or a day? Make your own guess about the kinetics. I will test it for you now. Here I have water within bottles of the same size and shape. One is an opened and the other is an unopened bottle of purified water. The opened bottle has a slight amount of impurities in it, like mineral deposits. Let's see how fast these two types of water would freeze in my freezer. The opened water froze in about 6 hours later. The unopened purified water froze after over 10 hours. Have you guessed it right? Why the freezing time takes so long and why it's different between these two bottles? Let Masood explain this to you.
Hi, my name is Masoud Razavi, a postdoctoral research associate at UW-Madison. As you observed in Enron's experiment, it takes longer for unopened purified water to freeze compared to the opened purified water. The only difference between opened and unopened water is the presence of impurities in the opened water. So, we can conclude that the presence of impurities somehow facilitates freezing of water. Now, I'm going to explain the physical reason behind the quicker freezing of opened water. Freezing of water is a process in which liquid water transforms to solid ice. In a more inclusive language, this phase transformation is called crystallization. During crystallization, disordered liquid turns to ordered solid material. Crystallization involves two steps: nucleation and growth. Nucleation is the starting step of crystallization in which the beginnings of solid phase are formed. In the second step, more liquid molecules attach onto the nuclei that are formed in the nucleation step to form bigger crystals. During crystallization, depending on the presence or absence of impurities, we can have two types of nucleation: homogeneous nucleation and heterogeneous nucleation. In homogeneous nucleation, nucleation is taking place in the bulk of material, and molecules of liquid phase are somehow getting together and sitting on each other to form nuclei. But in the heterogeneous nucleation, molecules in the liquid phase, instead of sitting on themselves, are attaching onto a surface of another material that could be particles from impurities or surface of container. So, in homogeneous nucleation, precursors can easily be formed based on the already existing surface. Therefore, we can predict that all the other conditions being the same, crystallization with heterogeneous nucleation should be easier than crystallization with homogeneous nucleation. This is exactly what happened in Enzarn's experiment and caused different crystallization kinetic characteristics of opened and unopened purified water. In opened water, due to the presence of impurities, the nucleation is mostly heterogeneous, meaning crystallization of water should be faster. Meanwhile, the unopened water lacks those impurities and nucleation sites and needs to undergo homogeneous nucleation, meaning that it should take longer for unopened purified water to crystallize.
Hi, I'm Megan Tracy, a graduate student at the University of Wisconsin-Madison. I'm going to show you another experiment you can do at home to test heterogeneous nucleation. In the previous experiment, we saw how you can cool liquid water below the freezing point at 0 degrees Celsius, making what we call supercooled water instead of ice crystals, due to the time it takes for the water molecules to rearrange and the unfavorability of starting that new crystal phase within the water. This time, we will see the effect of a pre-existing nucleation site on supercooled liquid water. For this experiment, you will need an unopened bottle of purified water, a dish, bowl, or cup partially filled with tap water, and some space in a freezer. Like Masood told you earlier, this process is rather sensitive to impurities in the water, which is why it's important that you use a new bottle of very pure water. To start, place your half-full dish in the freezer for several hours to ensure that it freezes completely. Once the dish has been in the freezer for a while, put your bottle of pure water into the freezer. You'll want to leave the bottle in the freezer for about 3 hours to give it enough time to cool from room temperature to below 0 degrees Celsius, but not long enough to crystallize, like we saw in Enron's demo. Carefully pull both the bottle and the now frozen dish of water out of the freezer and set them on the counter. This part is tricky because it's very easy to jolt the bottle and crystallize the supercooled liquid. Gently unscrew the bottle cap and slowly pour a bit of the supercooled water on top of the surface of the ice. Doesn't that look cool? As the supercooled water comes into contact with the existing ice crystal, it quickly turns into more crystals, even though it stayed as a liquid below the freezing point for some time while it was in the freezer earlier. Next, we're going to show you a way to prevent the crystallization of water in your freezer altogether.
Hi, I'm Ben Casting. In part 1 of this video, we showed you how to control how fast water freezes, affecting its kinetics. Now, we're going to show you how to control whether this process happens at all.
Hi, my name is Marie Fiore, and I'm a graduate student at the University of Wisconsin-Madison. We've just spent a lot of time talking about how water freezes. Now we're going to think about what happens when you mix something else in the water. Will it affect how the water freezes? We talked about how dissolving small amounts of a material, like the minerals in tap water, can make water freeze faster by giving the crystals a place to begin growing in the process that Masood described called heterogeneous nucleation. Here, we want to see what happens if we dissolve a lot more of something in water, like enough to change the way the water tastes. When we dissolve salt in water, that will lower the freezing temperature of the salty water. I'll show you this now, and we'll talk about why that is a little later. Since I only have one temperature in my freezer, we'll be able to do this by watching how long it takes for the ice to freeze. Here's what we'll do. Now we're going to talk about an experiment that you can do at home to see freezing point depression in action. So what I've done is made a series of salt solutions and put them in my ice cube tray so I can freeze lots of different things at once. On this side, I have just normal water, no salt in it, straight out of my tap. And then I've increased the amount of salt in each solution as we go across the tray. So I mixed 1 tablespoon of salt into a pint of water, 2 tablespoons of salt into a pint of water, and 3 tablespoons of salt into a pint of water. But you can choose the concentration that you want to experiment with. I'm going to put these in the freezer. When you do it at home, check it every 5 or 10 minutes or so to see what happens. We'll check in on it soon. It's been about 45 minutes and we're going to take a look at our ice cube tray now. Okay. So remember, this side is pure water, and on this side we have our saltiest solutions, and everything in the middle is somewhere in between. So the water has frozen solid, and the slightly salty solution definitely getting frozen, a little slushy. And if you look really closely, I don't know if you'll be able to see this on the video, but this second most salty solution, we're getting some ice crystals growing in, whereas the saltiest solution, still a liquid. So I'm gonna put this back in the freezer and see if it freezes anymore. But the next question I have is if it's possible to make a solution so salty that we lower the freezing point beyond the temperature of my freezer. So my freezer is about -10 degrees Celsius. So the question is really, can I make a salt solution with a freezing point that's lower than 10 degrees Celsius? So about 5 hours ago, I prepared 2 glasses of water. So one is just a glass of water. The other is 300 milliliters of water that I mixed 5 tablespoons of salt into. So these have both been in the freezer for about 5 hours, and we can see that the water is frozen completely solid. The salt solution, I'm not going to dump this over because it'll just be water all over my kitchen floor. But we can see we've given it plenty of time to freeze and lots of places for the crystals to nucleate. There's 5 tablespoons of salt in here. So time is not the issue. The problem is that the freezing point is just below the temperature of my freezer. So I'm going to turn things over to Kai Chen to tell you more about why.
Hi, I'm Kai-Chen Gu, a postdoc researcher at UW-Madison. Hope that you're having fun exploring how the different concentrations of salt affects the freezing behavior of water. Let us now try to understand these effects from the phase diagram of water with dissolved sodium chloride. A phase diagram describes the stable phases present at different conditions. The thermodynamic equilibrium phases are determined by the composition, which is on the x-axis, and the temperature, which is on the y-axis. The different color regions on this diagram represent different phases at specific temperatures and composition. First, let us start with pure water at room temperature and cool it down, following the red arrow. Ice can start to form at 0 degrees Celsius or below, consistent with our experience. Now, let's start with a solution of a 17 weight% sodium chloride, which is a liquid at around 10 degrees Celsius, again, consistently. As we cool down the solution, the points start to shift downwards and hit a phase boundary between liquid and ice at around -10 degrees Celsius. The ice consisting of pure water will start to form while the remaining salt solution gets more concentrated. At -21 degrees Celsius, your entire sample will be ice with the last droplet of salt solution solidified. This point at -21 degrees Celsius is also known as the eutectic point at 23 weight% sodium chloride solution. Lastly, if you start with a solution with a eutectic composition at 23 weight% sodium chloride, then it will not freeze at all until at -21 degrees Celsius. Such phenomenon of lowering the temperature at which water freezes is called freezing point depression, as Marie introduced earlier. Below -21 degrees Celsius, sodium chloride solutions of any concentration will be solid. The temperature at our freezer at home is typically around -18 degrees Celsius. Therefore, depending on the salt solution, you could witness your sample to be entirely solid, entirely liquid, or a mixture of liquid and solid. Interestingly, the definition of the Fahrenheit temperature scale also has to do with the freezing point depression. The scientist Daniel Gabriel Fahrenheit first determined the 0 point in Fahrenheit by placing his thermometer in an equal mix of ice, water, and salt. In his case, he used ammonium chloride. Although the Fahrenheit temperature scale is now commonly defined by the boiling and freezing points of pure water.
Hi, I'm Ben Casting, a graduate student at UW-Madison. You're probably already familiar with a very practical application of freezing point depression, salting roads and sidewalks to remove ice. Another practical application of freezing point depression is antifreeze for vehicles. Antifreeze is mostly a mixture of equal parts water and ethylene glycol, plus some additional additives. What do you think the freezing point of this solution is? The freezing point of antifreeze can be less than negative 34 degrees Fahrenheit.
Hi, my name is Mark Ediger, and I'm a chemistry professor at the University of Wisconsin-Madison. We hope that you will enjoy trying some of the freezing and crystallization activities that we have shown in this video. Hopefully, you will see for yourself that liquid water can exist below its freezing point. We can understand the behavior in this video by considering both thermodynamics, that's what's possible, and kinetics, that's how rapidly something happens. Enron and Masood showed you that low levels of impurities can speed crystallization a lot, and Megan showed you that water crystallizes really rapidly on an existing crystal. These are examples of changes in kinetics. On the other hand, Kai Chen and Marie showed you that high levels of salt actually lower the freezing point. So this is a change in the thermodynamics. And Ben reminded you of the practical applications of this freezing point depression. You may wonder, what do we all do when we aren't making videos? The students that you have just met are pursuing research projects to understand how to make new materials with the best possible properties. In this work, we find it really useful to think about kinetics and thermodynamics. In particular, we study how to improve the properties of polymer films, how to make them tougher so they don't break when they're stretched or bent. We also study how to improve the very thin films used in cell phone displays. Our research is supported through grants from the U.S. National Science Foundation and the U.S. Department of Energy. We thank you, the taxpayers, for investing in fundamental research that can influence the future.